As usual, the first part is just to import what we need, which is simply NumPy and TensorFlow. And then we're going to set some verbosity just to give us some output for logging. So we just want to log some info that is produced by our model as it trains. And then here's our first component, the model function. So for this, we have features, labels, mode, and params. One thing to note, and this is important, is that params needs to specifically be called params. This is just a TensorFlow thing. That's the argument that it's going to be looking for with our estimator. If that's not there and specifically called params, then they won't be passed. And the first thing that we're going to do is create our input layer. For the input layer, we're going to call a reshape on our features. That reshape is to prepare it as an image for the convolutional. So naturally or normally, it's going to be just one long vector. So for these images, they're 28 by 28 pixels, and so that's what we want to reset them to. So here, this -1 is going to just be for our batch size. So it'll dynamically reshape our tensor based on what the batch size is. And so we have width, height, and then the number of channels. The number of channels are for color channels. These are just black and white images, so they only have one. If you had full color, say RGB, then that would be 3 channels. So this is our input layer. It's really just a reshape of our data, our features X. And our features will be passed in as a dictionary, so it's going to be looking for X. And then our first convolutional layer right here, we're going to be computing 32 features or feature maps. And we're going to use a 5 by 5 filter for this. And our activation will be a ReLU. The ReLU, or the rectified linear unit, is a very common activation function, mostly used these days in convolutional neural networks or deep learning. Overall, it just behaves really well. Now the input tensor shape is, of course, as we've already discussed, batch size 28, 28, and 1. The output tensor shape is going to be also 28 by 28 and 32. The reason it's going to still be 28, 28 is because of this padding equals same. If we didn't want to have padding on it, and we didn't need to preserve the width and height, then we would use valid. So if we did this, we would have to change some of these different shapes, such as the input shape for our pooling layer and layers on down. What the padding does is it basically just adds zeros to the output feature maps in order to preserve the actual shape. One thing I should actually mention also is the 32. This is the number of filters that we're creating. So 32. And the kernel size, this is our 5 by 5. So we're going to pass this in as a list. And that's the shape of our actual filter. So 5 by 5, and this is where we assign that. We've already gone over the padding, so we'll skip that. And then we tell it the activation function, which is the TensorFlow ReLU function. Let's move on to the first pooling layer. In this case, we're going to use a 2 by 2 pooling. So this is going to downsample using 2 by 2 sections. And the stride, this determines whether or not there's overlap, and we can also skip pieces if we wanted to, but that's not a normal thing to do. So having a stride the same length as the shape of the filter ensures that there's no overlap. And the input shape is going to be the same size as the output we've already mentioned before, and the output size is going to be 14 by 14 by 32, and that's because of the 2 by 2 downsampling. So remember that a 2 by 2 filter with a stride of 2 is going to cut the image size, both width and height, in half. And we define this using max pooling 2D. We use the 2D because this is a two-dimensional image. You can ignore the batch size and also the channels. It doesn't matter. We just need the max pooling 2D. And the input, of course, is going to be our convolutional layer. And here's where we set the pool size and strides. Next, we're going to create another convolutional layer, and this one is going to give us an output of 64. That's because we're going to actually create 64 filters on this one. And we set the input to the previous layer, which is the pooling layer. Set the kernel size, set the padding, and set the activation. Again, we're going to use the ReLU function. And of course, once more, we're going to create another pooling layer, and this one is going to produce an output of 7 by 7 by 64 because we're using a 2 by 2 pool size again, which is going to cut our 14 by 14 in half. And the last thing that we need to do before moving on to some dense layers, as we've already discussed, is to reshape or to flatten. So in order to actually flatten to send into our dense layer, we use the TensorFlow reshape, pass in pool2 because that's what we're reshaping. We need the -1 for the batch size, and instead of adding the other dimensions, we have the input of 7, 7, and 64, but we need this to be a vector. So we have our batches and then our flattened images. So these are going to be 7 times 7 times 64. So you just multiply all of the previous shapes from here to get our flattened shape. Next we create the dense layer using just the tf.layers.dense. And of course our inputs will be our flattened layer that came out of or after our last pooling layer. We're going to set the number of nodes, or in this case it's called units. We're going to set that to 1024. So we're going to create over 1,000 nodes for this dense layer, and we're going to set the activation function again to ReLU. Next we have a dropout layer. We didn't mention this before, but dropout is something that helps to overall create a more generalized model. It helps to prevent overfitting. So what the dropout layer does, in this case we have our dropout rate of 0.4. Here it says we have a 0.6 probability that the element will be kept. Another way to put that is we have a 0.4 probability that a particular element in the input to this dropout will be dropped. So it's going to essentially be ignored in our model. And training, we need to set that, or we need to just say training equals mode equals this. So what this part does is the highlighted portion will be true if we're in training mode. So we need to let this know if it's in training mode because that is the only time that dropout is actually active. So if we're in evaluation or prediction mode, we don't actually use the dropout. And moving on, this is where we create the logits layer. This is basically just our raw output. So logits is going to be coming from another dense layer. And the inputs will be the dropout. And we're just going to set this to 10 units because we are classifying 10 different digits, 1 through 10. So again, logits, just the raw output. And here, we're going to create the predictions dictionary. We mentioned this briefly before. The predictions dictionary is going to be used for outputting anything in prediction mode. So we have the actual class predictions as the first part. So in this dictionary, we'll call it classes for the key, and then the actual value will be the argmax of our logits. We could also do this on softmax if we wanted to, which we see here, but there's not really a need for that just for the actual predicted classes. And axis equal 1 is important because each will be a vector and we need the axis 1. Then probabilities, this is another key, and this is where we'll also get the probabilities using a softmax function. This softmax basically squashes everything into actual probabilities, whereas the raw logits will not be in that form. And so this way we can not only see the actual predicted classes, but we'll have the probabilities of each of the other classes. Now that we've created the predictions dictionary, we also want to say if the mode is predict, and we specifically need the tf.estimator.modeKeys.predict. And again, that's because our actual estimator is going to be using this value. So if that's our mode, then this is the end of our function. And we're just going to return this estimator spec for the mode being predict. And we want to say that predictions equal predictions. So it's going to use this output for the dictionary as the estimator output. So if it's not mode, then we'll continue on, and we're going to start by calculating loss because that's done whether the mode is train or evaluate. And this is the part where we need to create the one-hot labels from our class labels. So we're going to use the TensorFlow one-hot method, and our indices, we're going to cast the actual label values as tfint32. That's just in case it is in another form, we'll create that cast. We don't want int64 or int8, anything like that. We want int32, it's going to perform the best. We also want to make sure they're not float. And the depth, that's the number of classes that we have. So these are going to create one-hot vectors for each of the class labels. And let's define our loss function. In this case, we're going to use softmax cross entropy. We're going to use softmax cross entropy because it's going to operate on the logits, and we want to perform the softmax inside of that actual cross entropy function, because this function produces or performs that a lot more efficiently than if we fed a different cross entropy function actual softmax outputs. So we use this on the logits. And we're going to say that the one-hot labels are those that we already created, and that logits are logits. Here we configure the training op for the actual train mode. So at this point, we're going to say if the mode is train, then we're going to define our optimizer. In this case, we're going to use just a standard gradient descent optimizer and pass in a learning rate. In fact, this actually we should have created, or I should have created, as a parameter to be passed in. So instead of hard coding that, we could have used our params. So we would pass in a dictionary for params, and one of the values would be learning rate. And so then in this case, we would actually use params with the key of learning rate for this. And our actual training op, this we want to use optimizer, which is the optimizer we just created, and we specifically want to minimize on our defined loss function. And then our global step, this is going to be get global step. Really, that's just so that the logging can keep track of the actual step of the whole graph. And that's for logging purposes so that you can pick back up where you left off. And so if the training mode, or if the mode is train, then at this point we also return this estimator spec, and that would be the end of the function. And that'll be with mode, loss, and our now defined training op. But otherwise, if it's not the training mode, here we are, and we're going to create our evaluation metric, which in this case is just accuracy. We could add some others if we want. This is a dictionary, so we can fill those different values. So in this case, we use the TensorFlow metrics, and specifically accuracy. And we just pass in the necessary values, which are the labels and predictions. And we need the classes in order to compare.